am I? Okay, let's jump right in then. So the idea is between today and tomorrow, we're going to finish 2.2. So we'll get as far as we can today, and then we'll zoom on over to 2.2 when we can, and then get through that. And that'll be the goal for this week, to get through 2.2. So here we go. Let me find my completed packet so I don't leave anything out that I want to talk about. Okay, so this section is all about functions because we're going to spend the whole chapter talking about functions. So we need to figure out what is a function. How do you tell it's a function? So section 2.1 is going to talk about how do you tell if it's a function algebraically? How do you tell if it's a function from a graph? How do you tell if it's a function from points? All these different ways that you can tell, okay? Everything you really never wanted to know about a function is what you're going to learn. So before we talk about functions, let's talk about relations. Now, you know, you guys do not have to know definitions, but sometimes it helps you see the big picture. So a relation is just a set of ordered pairs. So this is a set of ordered pairs. This is a relation, okay? And a set is just a bunch of stuff with curly brackets around it. So you've got a curly bracket. Remember, that's the little squiggle frame. You've got some ordered pairs. Remember, those are just x, y, x, y, x, y. They're just points on a graph. And then you got a squiggle. So that's a relation. Okay, now, not all relations are functions. Some of them are. So we need to tell, how do you know if a relation is a function? Okay, one thing we can do is we can make a mapping diagram. So that's what these guys are. Sometimes they're ovals, sometimes they're big rectangles. But what we want to do is we want to put all the x values into one oval, and we want to put all the y values into the other oval. That's what we're going to do. So if we go up here, remember this is x, y, x, y, x, y. You don't have to just put them in the order you see them. You don't need to list them numerically or anything. So we're going to do 1, -1, 2. Okay. And then we're going to go over here and put all the y's. So we're going to have 2, 3. Now I don't have to list the second 2 because I already have a 2. So you don't have to repeat it. All right. Then we're going to connect them with lines, whoever goes together. So in this first pair, 1 goes with 2. There. Second pair, -1 goes with 3. There. Third pair, 2 goes with 2. There. Okay, you made a mapping diagram. You put all the x's in one, all the y's in one, and then you connected them with lines so we know who goes with who. Now, I know that looks so silly. It looks like something you do in first grade, right? But there's a reason we did it. We're going to get there in just a second. Okay, now you guys also know the definition of domain and range. You learned that a long time ago. So you know the domain is all the x values and the range is all the y values. So this whole little oval is the domain. And this whole little oval is the range. So it's another way to really see at a glance the domain and the range, right? The difference. Okay, we can also write them with the little squiggles. So we can do a squiggle and we can write all the x values. There's your domain with a little squiggle. We can write the range. And again, you don't have to repeat them with the little squiggle. So there's our domain, there's our range, just another way to write it. We also know domain, since those are the x values, that's what you would put into an equation. And the range, the y value, that's what you would get out. That's what you would solve for. So it's another way of kind of looking at it there. All right, so we made this really nice little mapping diagram of this relation. Now let's talk about how do we know if it's a function? Okay, I'm going to scoot it up a little bit here. Here we go. Is the relation a function? All right, well, a function is a relation in which every element in the domain corresponds to exactly one element in the range. Okay, what does that mean? That means every single x has a y paired with it. Okay, everybody has a friend. That's the first rule. Second rule is that it only has one friend, okay? Every X only goes with one Y. We can't have X's going with a bunch of Y's, okay? That's what that means. That's the definition. So what this says is each X has an arrow, or every X has an arrow, however you want to write it. Every X better have a line coming out of it. And they better only have one line coming out of it. Okay, that's the deal. Oh, each. Sorry, honey, I know it's small. Each X has an arrow and only one arrow. So if we go back and we look at this for just a second, okay, I'm not worried about what's going on with the Y's. That has nothing to do with whether it's a function. I'm only looking at the X's. X controls the situation. Does every single X have a line coming out of it? Yeah. Does every single X only have one line coming out of it? Yeah, he's got one, he's got one, he's got one. This guy is a function. So turns out, yes, he's a function. Perfect. Now, notice one of the Y's has two lines. See that? That's okay. We don't care what happens. Once those lines leave the domain, they can all go to the same Y. What we care about are the X's. That's what we care about. Okay, every X has one and only one line coming out of it. If they all go to one number over here, who cares? But that's the definition of a function. One line and only one line for every single one. Okay, so let's just talk about this real quick then at the bottom. So when do we talk about Y? We don't. Does it matter if the Y value is repeated? No. Does it matter if the X value is repeated? Yes, you can't have your X values repeat. So that's kind of the situation there. All right. So every X has one line and only one line coming out of it. All right. So let's move on to the next page. We're going to play a little game called Is the Relation a Function? Yay. All right. Everyone's favorite game show. Okay. Here we go. Is the relation a function? Okay, there you go. All right. So we have little mapping diagrams, right? These are rectangles instead of circles. And they're not all numbers. So basically the takeaway from this is just whatever's on the left better have one line coming out of every single item on the left, right? So let's look at this first pair, this first little relation. Is this a function? No. Why isn't it a function? B doesn't have a line. No line. No line, so not a function. Okay, awesome. All right. Now let's look at the middle one. Is this a function? Yeah, he's a function. Okay, why is he a function? Okay, so I'm covering up the right. I don't really care what goes on over here. They can all go to the same person for all I care. What I care about is every single X has a line and only one line. Works for me. What about this one over here? No. What's wrong with him? Who's messing it up? C's messing it up. Okay, because everybody has arrows, which is great, except that C has how many? 2. That's what's messing it up. There's 2 arrows coming out of C. That means C is repeated if you were to write those ordered pairs. That's why he's not a function, okay? Because C is repeated. So on your test, you're going to be given some different mapping diagrams and ordered pairs and things like that. And you're going to be asked, is this a function? And you just have to tell me yes or no, okay? So mapping diagram, that's how we would do it. Okay, let's look at this next one. Now we don't have a mapping diagram. Now we just have a little set, a little relation, a little ordered pairs there. Can we figure this out? Sure, okay, because the idea is every X has a Y. Well, that's true. And the X's are not repeated. Every X is only used once. So knowing that information, is this a function? Yeah, he's a function because what I notice is, first of all, every x has a pair and the x's do not repeat. Now, some people, they're like, oh, that's kind of confusing. So if you wanted to, you could draw a little mapping diagram on here and you could map it. You could take all the x's, 1, 2, 3, 4, and you could take all the y's, 4, 4 repeats, 5, 2, and you could map it and just make sure. So 1 goes with 4, 2 also goes with 4. That's okay if y repeats, that's fine. 3 goes with 5, and 4 goes with 2. And then sure enough, every x has one line and only one line, so it's definitely a function. So you can always draw a map if you get confused about the points, okay? But you were looking for x's that do not repeat. So, oh, yes, it's a function, yeah, okay. So the takeaway from this is this little bold line right here. If the x values are repeated, the relation is not a function, okay? We do not want x to repeat. All right, now it wants us to find the domain. So it already did the curly brackets for us, which is great. So you don't have to draw your squiggles, okay? So what would my domain be? 1, 2, 3, 4. Those are my x values. What would my range be? 4, 5, 2. Perfect. Okay. Perfect. All right. Everybody okay with that? Okay, let's try it again. Same thing. Now you can draw the mapping diagram if you want to, or we can look at the fact that if the x values repeat, it is not a function. Okay. So I already heard not a function. Everybody agree with that? Not a function. Who's messing it up? Who's the number that repeats? 1. You've got 1 repeating. That's the problem. So because they repeat, it is not a function. That's the situation. So again, if you wanted to, and some of you don't, you're happy with learning the way you learned it. Here's 1, then 1 repeats, 2, 3, 2, 4, 3, 5. There's our y's. 1 goes with 2, 1 goes with 4, 2 goes with 3, 3 goes with 5, and there's the problem. Sure enough, there's 2 arrows coming out of 1, and that's the issue. Okay, so every input, that's the x, must have exactly 1 y, 1 output. Okay, good deal. So we learned how to tell if it's a function from a mapping diagram. We can tell if it's a function from ordered pairs. Now let's look at graphs, okay? You guys probably remember this. How do you tell if it's a function from a graph? The vertical line test, the good old vertical line test. So you can use your pencil, you can use your finger, you can use whatever you want, but make it a straight vertical line. And what you're gonna do, not this, okay, is run that little vertical line from left to right across your graph from left to right and see, does it touch your graph in only one place at a time? If it only touches your graph in one place at a time, you're a function. If it touches your graph in 2 places at the same time, you're not a function. Okay, so here we go. Let's try this dude right here. Okay, so I'm running it across, or I'm making a bunch of vertical lines, and I'm touching the graph and touching the graph and touching the graph, but I'm only ever going to touch it in one place. Does everybody see that at a time? So that means he's a function. Yay. Okay. So what that means here is every vertical line intersects the graph only once. Okay, that's just kind of a mathy way to say it. I just copied and pasted that out of your book. All right, now let's look at this little arc, this little piece of a circle. Okay, as you run your vertical line over there, some places are fine. Like look right here. These are perfectly fine vertical lines that only hit once. But then when you start to get over here, what happens with your vertical lines? you touch it in two places at the same time. Does everybody see that? And if you touch in two places at the same time, he is not a function. Okay. So let's talk about a couple of things that you would, encounter, a couple of different graphs. So obviously a big no-no is a circle. Any kind of a circle, you're going to touch that circle in two places at the same time with a vertical line. Any kind of a piece of a circle that wraps around the side, like this guy, you're going to touch it in two places at the same time. What if your piece of the circle, though, only goes like this? What if this is your piece? Is that a function? Yeah, he's fine, right? Because you only touch one place at a time. So it has to be something that kind of wraps around like this on the side. Sometimes they'll use a parabola that looks like it's fallen over like this, like instead of going up and down, it's like, and it fell over. Is that a function? No, because you can touch it in more than one place at one time. Now, speaking of parabolas, let's talk about those, the real deal parabolas, the parabolas that open like this and the parabolas that open like this, because that's what we're going to spend a lot of time talking about. Well, no, that's the next chapter, but it's coming. Those parabolas, even though a lot of teachers draw them, including myself, a lot of times teachers draw them like this, right? And they look almost vertical. So they look like maybe they're not a function. Do parabolas go straight up, or do they kind of, no, I'm already seeing heads. They kind of ever so slightly open up like this and they turn into a bowl. They turn into a bowl. So whether they're down or whether they're up, they are functions. Parabolas are always functions unless they fell over like this. This isn't technically a parabola, but we kind of call it that in algebra. When you get to trig, you'll figure out he's not, he's parametric. But anyway, the ones that go up like this and the ones that go down like this, those are functions because they're not going straight up. They're ever so slightly getting bigger like a bowl, okay? So that kind of gives away the next question there. But so in my math lab, unless it's been changed on me, there used to be a question either in the quiz or the homework that would ask you to complete the definition of the vertical line test. So this is the definition that my math lab would want. It's super wordy and it was really hard for students to figure out. I couldn't figure it out either. I kept getting it wrong because it sounds like they're a lawyer. You know how lawyers kind of talk like really fancy and they say things, but you're not sure what they're saying. So if no vertical line can be drawn so that it intersects a graph more than once, the graph is a graph of a function. Okay, so if they want a definition and they're leaving blanks, that's the definition they want. So just fill in the blank with those words so you can complete it. But what basically is happening is if the vertical line intersects your graph twice or more, right, it's not a function. Okay, so let's look at these two down here at the bottom then. All right, we have a little oval, a little ellipse, okay. Is this a function? No, definitely not. Because, I mean, every vertical line you draw, it only takes one, but every vertical line you draw is going to intersect it at more than one place. Okay, I already gave the answer away, but what about the little parabola down here? Is he a function? Yeah, we said he was. Any vertical line you draw should only intersect him in one place at a time. So he is definitely still a function, okay? All right, so we can do ordered pairs, we can do mapping diagrams, we can do graphs. Now let's go to equations. What if I just give you an equation? Can you tell me if the equation is a function or not? Okay, I know it's exciting stuff. Okay, here we go. Is the equation a function? Okay, so to determine whether an equation defines y as a function of x, you're going to solve for y. That's your first thing you're going to do is get y by itself on one side. All right. Then if two or more values, this should say of y, can be obtained for a given x, it's not a function. What in the world does that mean, Ms. Holcomb? Okay, that means any even power on y means it's not a function. So if y is squared in your equation, not a function. If y is raised to the fourth, not a function, okay? What if y is just y raised to the 1? It's fine. What if y is raised to the third? He's fine. It's any even power on y, okay? Any even power on y. And let's figure out why this is. So what that really means is if you had x equals y squared, okay, and you take the square root of each side, okay, then what is really happening is this. And then you've got that x could equal the positive y, or that x could equal the negative y. So you have two lines coming out of x. You have x repeating there. And that's the issue. That's why that is. Okay, because if you were to map it, you've got root of x over here, and you've got y and negative y over here. Sorry, that should have been root. You've got a line coming out of each one. You've got that x repeating, okay? So we've always been really focused on x, right? X can't repeat. It's x, x, x. Now for equations, we're shifting this to y. We're shifting it to y. He's the one that has to handle this because of this situation. So any exponent on x is fine, but an even power on y means it's not a function, because when you take the square root of both sides, you're going to have one x equaling two y's, the positive version and the negative version, and that's what messes you up. Does that make sense? Okay, so it's a little confusing that we have to switch to y, but that's the rule. Okay, so let's try it here. Is it okay if I turn the page? Okay. All right. Okay. So is the equation a function? Okay, so remember the rule is y cannot have an even exponent. Okay, if y has an even exponent, it's not a function. That's the bottom line when it comes to equations. So we're no longer looking at x, we're looking at y. Is this a function? Yeah, he's a function. Okay, why is he a function? Because y has an exponent of 1, so he's good. We don't have that weird situation happening where if we were to solve for it and take the square root, we have two versions. Okay, what about this one? Is this a function? No, because of the y squared. Okay, so I know it's a lot of weird rules, but your homework, you'll just be practicing that a lot. Yes, no, function, yes, it'll go quick. Okay, so now that we kind of talked about what is and what isn't a function, let's talk about function notation. You guys know function notation. Okay, yeah. Function notation means if it is a function, I can replace the y with f of x, meaning this is a function of x, right? So this is function notation. You read it as f of x, okay? This just means that the variable x is being put into the function, Okay, now I kind of mentioned this to you before, but I haven't had to do this year, but before the pandemic, I would have night classes with adults that were not super smart teenagers. And so they had not taken math in a really long time. And so if you can imagine like your mom or dad or grandma trying to take college algebra, it's a struggle. Struggle's real. We go real slow. And they know that parentheses mean multiplication. So in their world, Function notation is real tough. We spend a long time trying to talk about function notation because they are really sure that I am multiplying the letter F by the letter X. So it takes us a long time to talk about that we're not multiplying anything. So this next little sentence is for them. It's not for the smarty pants in the room. The parentheses here do not mean multiplication, right? They just show us what's being put into the function. That's all. You guys know that. It would never occur to you to think that. You've been dealing with function notation your whole life, but you know, grandma hasn't. And so you got to really be a little patient. Okay. All right, here we go. So let's evaluate the function. Okay, here's our function. How do we know that's a function, by the way? Because it says f of x. Anytime you see f of x equals, it's a function. They've already told you it's a function. So it's kind of a little cheating way to know that. Okay, we want to evaluate. So in this case, this is telling us x equals what? 2, right? Because this is f of x. So x is 2. They want you to take this function that you saw up here and they want you to put 2 in for it and for x and give us the answer. Okay, easy enough. So f of 2, first we want to square 2. Then we want to minus 3 times 2. And then we want to add 7, right? So we've got 4 minus 6 plus 7. Everybody get a nice little 5 there? Okay. 4 minus 6 plus 7. This would be negative 2 plus 7. We get our 5. Okay. All right. Let's look at the next one. Next one wants us to keep x in. You've been doing this stuff for years with numbers. Now we're going to start putting some other stuff in there instead. Instead of putting in a 2, we're going to put in a negative x and see if that changes it. All right, here we go. So f of negative x means, and notice he's in parentheses. Well, he's always in parentheses, but you want to keep him in there because you don't want to lose his negative. So this is going to be negative x squared minus 3 times negative x plus 7. Okay, let's see what this shakes out to be when we clean it up. Okay, positive x squared, because you know if you have negative 2 and you square it, negative 2 times negative 2 is 4. Okay, so what would negative x squared? Negative x times negative x would be x squared. So that's not going to change at all. Okay, let's look at this. What about minus 3 times negative x? What's that going to turn into? Positive 3x. And there's our answer. And then the plus 7 in the back didn't change at all. Okay, so we just kind of modified it a little bit. Everybody okay with that? That's the best we can do. All right, let's get a little bit more complicated then. Let's try this one. We're going to put in x plus 2. All right, this is going to be a little work. All right, again, leave it in parentheses. You can already tell by that first term you're going to have some work because what does that first term mean? FOILs, 2 of them. Yeah, okay. Minus 3 times your little x plus 2. We're going to have some distributing to do there. And plus 7 in the back. Okay. All right, let's clean this up. We know this really means there's 2 of them. Okay. Then I'm going to go ahead and distribute this negative 3. Watch your signs. Okay. Everybody all right with that? Okay, now I'm going to FOIL this out. I'm going to get x squared plus 2x plus 2x plus 4. And then I still have minus 3x. Now, instead of putting minus 6 plus 7, is it okay if I go ahead and handle that and put a plus 1 in the back? Is that okay? I just combined those two, that negative 6 plus 7 in the back. Okay, I still have to clean up some more. All right, x squared does not combine with anyone. All right, I have 3 x terms here. I have plus 2x, that's 4x, minus 3x, that would just be plus 1x. And then I have plus 4 plus 1. That's just plus 5. And there's my answer. Okay. Everybody okay with that? So we did a lot of evaluating functions here, a lot of inputs. We did a number, which you guys can do all day. We did a negative x, which is kind of interesting. And then we did a whole little polynomial, x plus 2, a binomial we stuck in there and played with it and came out with something else. So you're going to have to be able to do that, you know, and evaluate these guys and clean it all up and just take it one step at a time. Okay. So again, the section's all over the place. It's kind of the introduction section. We're going to go back to graphs now. All right. Now they're going to give you a graph and they want you to find the domain and range of the graph. And they want you to put it in interval notation. Okay. So let's think about this. It's not always where the graph starts and stops. You can't take the easy way out, because sometimes the graph will go way over here and then come back this way and stop. Well, it's not from where it starts and stops. It's from where you see the whole thing, right? The whole span of the graph. So to find the domain, you're going to move from left to right, right? Okay, and find the domain. To find the range, you're going to start at the bottom and go bottom to top and find the range. And you're going to use interval notation, okay? So you're going to use parentheses if you see an open circle or infinity. Where would you see infinity? You would see infinities with parabolas, right? Because they go on forever. So in that kind of a situation, you would have to use infinities. Otherwise, you're always going to use those hard square brackets, okay? So only infinity or open circle get parentheses. Everything else is a hard bracket. Let's see. Remember x-intercept, that's where the graph crosses the x-axis. Y-intercept, graph crosses the y-axis. Okay, you ready? Let's do some problems. Okay, that's actually, this page 5 is the end of section 2.1. Okay, here we go. First graph. All right. So this graph is kind of strange because it has these giant filled in dots. Normally yours won't have that, but this one does in this case. Okay, students tend to struggle with domain and range with graphs. So we have to make sure we're really comfortable with this. All right, here's just our little doohickey here. I don't see any open dots and I don't see any arrows indicating infinity, which means my domain and my range are all going to use hard brackets. Okay, they're all going to use hard brackets. So here we go. Domain, range, they're all going to use hard brackets. We're going to put the smallest number and then we're going to put the largest number. Okay, and we're going to kind of make a cross. So we're going to go left to right, down and up. Okay, all right. So first thing we're going to do is go left to right. So if I'm starting on the left and I move along, the first time I encounter my graph would be -3. Does everybody see that? That's the first x value. Perfect. Then I keep going and I keep going and I keep going. What's the last x value? Don't say it's -1. Think x values. 0. And then there we go. Everybody good with that one? Okay. All right. So again, this is where the graph starts and stops worked nicely for the domain. But for the range, it doesn't. The range is not going to be a y value of this point and a y value of this point because the graph dipped down. See that? It dipped down a little bit. So to find the range, we're going to start at the bottom, the very bottom, -infinity. And we're going to move up and we're looking at y values. So the very first time I encounter my graph is -5 for a y value. And then it goes up, 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 up. And what's the last y value for this graph? -1. And there's your domain and range. Okay. So you can't just use the 2 dots that you see. You have to actually move through it and move up And as soon as you see it, what's that X value? What's the last X value? What's the first Y value? What's the last Y value? And you're good to go. Okay. All right, let's try this little dude. So he's a parabola. I see arrows. Am I going to have parentheses where his domain and range are concerned? Yeah, so just keep that in mind. Okay, here we go. First thing it wants us to find is f of 2. Well, I don't have an equation to plug it in, but I have a graph. What does this mean? What equals 2? This means x equals 2. What it wants you to find is y. Right? It wants you to find y. So I'm going to go over to my graph. Okay. So it tells me this tick mark is 5. So 1, 2, 3, 4, 5. They're all one little tick mark. Okay. So here's x equals 2. Okay. So if I go straight up, okay, remember my ladies that turn the paper, right? It's going to get you in trouble. You got to have the straight papers, ladies. Okay. Straight papers. All right. Mine's already a little crooked. Okay. Good. It ends up, y is 3. That's what it asked you for. Okay. All right, let's look at the next one. Now this one says f of x equals 0. What does f of x stand for again? Y. So this is telling us y is 0. What is x? That's what that question means. Make sure you can tell the difference in that, okay? All right, so where is y 0 on this? X-axis, right? So here's a y is 0. Here's a y is 0 for the graph. I got 2 of them. I'm going to have 2 of these values. So in this case, what is x for this dot? A -1. And then this dot over here, +1. Those are your x values. Okay. All right. Now it wants domain and range. Okay, so remember, this is going to be tough because you're going to have to really think a little abstract here. This parabola is not going straight up, right? Where is this parabola going? It's getting really, really wide, right? Really, really wide. So if I'm thinking about this thing getting really, really wide, and I'm coming from the left, how far does this go? How wide does this get? A parabola's domain, whether it's up or down, is all real numbers. It's -infinity to +infinity because it's going to keep on going forever. Okay. All right. Range-wise, though, okay, remember we start at the bottom. We're going up, 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 up. First time I encounter the graph, the y value is -1. That's going to be a hard bracket. It's not an open dot and it's not an infinity. Then how high does that graph go? Infinity. And because that is an infinity, he gets a parenthesis. Okay. Is that all right? Okay, let's look at x-intercepts. So remember, x-intercepts happen where, good. X-intercepts happen where it crosses the x-axis. So both of these are your x-intercepts. Okay, you can just write -1 and 1. You cannot write -1, 1. Is that an x-intercept? No, that's like way up here. That's just random point in no man's land. Now, if you want to write points, you can write them like this. That would be great, but you can't write -1, 1. Okay, what about y-intercepts? Yeah, there's just one. Remember, that's where it crosses the y-axis, so it's right here at -1. You can just put -1, or if you want to put a point, that would be 0, -1. It's this guy right here. Okay, let's finish this last problem and we're done. Okay, graph the given functions f and g in the same graph, same coordinate system, and then tell how it's related. So we're going to slowly start moving into translations. Remember where you move stuff around? All right, So you may not know this, which is why I wanted to do this, because my math lab is going to ask. So for the first graph for f of x, it wants the absolute value of x. Does anybody know what that looks like? It's like a V, a hard V at the origin. So you're looking like this. This would be f of x, okay? Just a hard V. Okay, g of x is absolute value of x minus 1. What does that mean is going to happen to your V? Down 1. It's going to move down 1. I know we haven't covered translations yet. I don't know why they put it in this section, but this guy here would be g of x. So how are they related? What happened to g of x? He started out as f of x, and then where did he move? He went down 1. G of x is 1 unit down. If it were in parentheses, yeah, if he was inside that bracket, he would have gone right, because it's the opposite of what you think. Okay, good. So now if you didn't know those graphs, you could have also plotted points, right? And plugged them in and come up with it that way, or put it in your graphing calculator. But I think that's the only one they ask you. Okay, well, that got us through section 2.1 somehow, even though Ms. Holcomb was off her game. So you can do homework 2.1. You can do quiz 4. And then tomorrow I'll record section 2.2 for you. Okay, and I'll send that out. So hopefully I'll see you tomorrow, but if I don't, I'll see you Tuesday.